Okay. All right. My name is Ali. I've been doing a lot of research and development in this area for some time, working on adaptive streaming clients. So the talk today is not going to be just specific to the Dash clients, but in general, ABR clients. Previously, I was at Cisco, where we were running lots of large-scale experiments with these clients. So I'm going to talk about four main subjects. What a streaming client does, how we are going to scale them in real world, the need for analytics, and some cool features that we would like to see in the near future. So as you know, this all started with Move Networks a long time ago, more than 10 years ago, actually, and they are no longer in the space. There was smooth streaming at some point. There still is, but hopefully it will go away very soon. Flash and HDS from Adobe, they're almost gone, right? And obviously, the elephant in the room is HLS from Apple. And then the new technologies, the maturing one is MPEG Dash, and the new one is CMAP from MPEG. For those who don't know, the Pentos draft from Apple and from MLBAM, hopefully is going to be an RFC very soon. So it's going to be almost finalized, meaning that they will not be just able to update the drafts whenever they would like to, right? So it's going to be pretty stable at some point. But that's mostly because Apple is now adopting CMAF anyway. All right. We have seen this picture earlier today. So basically what's happening here is we have a live or on-demand content. It goes through a transcoder or multi-bit rate encoder. There's a packager. And then everything is posted on the origin server, right, along with the manifest. So we have multiple representations of the same content divided into short duration chunks, segments, fragments, whatever you want to call them. And then the Dash client or any regular ABR client is supposed to get the manifest, and based on that manifest, is going to send HTTP GET requests to get the respective segments from the server. Everything is going to be pushed into the playback media buffer, and then when the timing is right, the decoder will start decoding them, right? The segments are obviously independently decodable, meaning that from switching one segment to another, hopefully there won't be much distortion or distraction on the screen. There could be resolution or bitrate change, obviously, because of adaptation, but if things are done properly, the clients will not really see a big difference from segment to segment. Now, what Dash standard is specifying the manifest format, as well as how the manifest is parsed on the client side, and then how the media segments are prepared and parsed on the client side, okay? The rest of the stuff, the HTTP stack, how we are going to transport the manifest, or how we are going to do the adaptation, they are not part of the standard. They are left for other specs, or they are not even defined anywhere. So mostly, when we are talking about a client, the media engines, obviously, they are also part of different MPEG specs, or if you are using an MPEG codec, that will be the respective spec for that. But then the HTTP client is defined bunch of RFCs, right? And frankly speaking, there are also some Dash clients out there who are not really using the HTTP stack anyway. The most interesting part here is the control engine, how the client is going to perform the specific tasks that we want them to do. So this is a typical Dash manifest. You get it from the origin server or from your CDN, and then you look into it, and then you are supposed to construct the URLs for each segment, and then ask them from the server one by one, right? Depending on the language, depending on the codec, whatever, right? As the client seeks to a different time, or it would like to, rewind or forward, obviously you need to figure out which specific segment that you need to ask from the server. Now, the main motivation behind adaptive streaming and doing the adaptation on the client side was to simplify the server so that they could easily scale to thousands or millions of subscribers, right? A typical CDN, a large-scale CDN, can serve easily millions of clients. You wouldn't be able to do that with RTSP clients if you have any experience with them. Those servers would be a lot more expensive, a lot more difficult to debug and maintain. So we have plain vanilla HTTP servers. You can buy an off-the-shelf server, install open source software, and it's ready to go, right? We are trying to push all the intelligence to the clients, hoping that they will do the right thing at the right time, and things will just work. So we have the request response mechanism, but I have a deep note over there that says you can also use multicast to deliver their segments if you want to. Multicast or broadcast. We are not going to get into the details, but that's another option. So it doesn't have to be just HTTP GET response. So the client is obviously fetching the manifest and parsing the manifest, and then it needs to use the OS provided HTTP stack. It's not part of the client. HTTP almost always runs over TCP, but it doesn't have to. The RFC doesn't say anything about using TCP. You just need to use a reliable protocol, which could be quick, which is also being standardized by the IETF at the moment. And if you are using a Chrome browser, and if you are not behind a firewall that blocks quick connections, you have been using quick for a long time, especially if you are streaming something from YouTube. And then the client also needs to have the decryption tools, DRM license, all that stuff, as the previous talk mentioned, right? And then the client is continuously monitoring and measuring a bunch of things. You know, size of the playout buffer, how much data it has in its buffer, both in terms of bytes and in terms of duration, right? We don't want to underrun our buffer because that means if we run out of data, there will be a frame freeze, right? That's not good. But we cannot overflow our data buffer either, because in that case we will start losing data as well. So we need to maintain a comfortable amount of data in our buffer. And then you need to monitor your download times. You ask for a segment, right? And then it takes you X seconds to download it. You need to figure out how much throughput you are observing from the network. You need to look into your local resources. You have sufficient CPU, memory. You know, is the window size minimized, maximized, full screen? Is it projected to a larger screen or not? That sort of thing. And then maybe you received everything. You have sufficient bandwidth, but something is wrong with the display or the decoder itself. So you are getting some dropped frames. In that case, you might want to take some action on that too. So based on all of this, client is going to perform the adaptation, and then eventually client needs to measure and report a bunch of metrics for analytics purposes. The client's task is not easy. It is always running a trade-off in terms of maximizing the quality or improving the quality stability, right? We don't want to have too much adaptation in short amount of times. And we would like to be as close as possible to the live programming, especially in sports. At the same time, we don't want to have too many stalls, frame freezes, and we don't want to wait too long when we are starting up the video stream or when we are seeking. Those are all different types of trade-offs that you need to pay attention to. Looking at the CTA Wave project, 3 types of clients have been defined: type 1, type 2, type 3. I'm not going to read all of them. What we would like to see most in the field is type 3, where you can actually use all the nice features of adaptive streaming, Dash or something else, through media source and encrypted media extensions provided by HTML5. We are also okay maybe with type 1, but usually type 2 is not a very favored model. And if you are asking how widely MSE is supported in today's browsers, you can go to this website and repeat the test, caniuse.com/search query MSE. You will see that a lot of browsers today, they actually support MSE without a problem. And some reference slides for your information, you know, what type of DRM is being supported on desktop browsers, and then on mobile platforms, you know, Android, iOS, and you know, other platforms. It's just for your reference. Now, I would like to get into some challenges we had over the past several years, and how we try to resolve these issues. So streaming over HTTP obviously was a big step coming from an RTSP or other proprietary streaming protocols. HTTP was everywhere, right? It was available from almost all CDN vendors. And video should be just an ordinary web content. That was the motivation for this work. And HTTP, although it doesn't have to, it always uses TCP. And TCP is a well-known protocol, probably older than I am, right? And many researchers, world-known researchers have been studying TCP for a long time. And it's internet-friendly, congestion-friendly, so it's fair bandwidth sharing, all that stuff. So normally, the expectation was everything should just work fine. Does it? Well, it doesn't in most cases. When it doesn't, well, I'll show you a couple of examples. If you're the only guy who is streaming over Dash or some another AVR protocol, and there is nobody else sharing resources with you, you are going to be okay. There could be other web traffic, FTP traffic, email traffic. There's not a problem. But if there are two of you, right, you are trying to watch something in your living room, your wife wants to watch something in the kitchen, and the kids would like to watch something else in the basement, then you get some problems because your clients are going to start interacting with each other, okay? If you have a 20 megabit DSL connection, if everybody wants to Netflix at the same time, well, you have a problem. And this is not really a very untypical issue, right? It's going to happen in your household unless you have a fiber connection kind of thing. And on a larger scale, it will happen on the ISP access and aggregation links. It might not happen on your DSL access link, but the service provider is going to experience this problem, especially during the peak times, when everybody is willing to Netflix something. Or if you go to Starbucks coffee, Apple Store, McDonald's, whatever, or airport, right, hotels, you have the same problem. Now, the paper we published in 2011, almost 6 years ago, was the first study that looked into different types of ABR clients at that time. We looked into HLS, Netflix, and the Microsoft Smooth Streaming client. So what we did was a controlled experiment to see how the client was adapting to different types of network conditions. So this is the bandwidth profile we applied to a single client. And this is what the client did in terms of the requests. As you can see, the client is asking for a lot of segments back-to-back to fill up the buffer as quickly as possible. That's what we call the buffer filling state. I don't like to call it buffering state because you are always buffering data. Buffer filling state is, I think, more correct. And then eventually, once you have about 30 seconds of data in your buffer, you get into the steady state where for every segment you consume, you need to get another one. Now, the client is doing a fairly good job, reducing the bitrate, increasing the bitrate over time. And what the client was measuring these chunk throughputs. You start the timer, you make the request, you download the segment, right? You know the size, you know your time duration that lapsed since the request time. You calculate your throughput, and those are your measurements. And what the client was doing, as we inferred from the data, just exponential moving weighted average. So that was okay. Microsoft never gave us the details of their adaptation algorithm, but reverse engineering gave us the details. Well, that was good. But then we said, okay, we are going to get 10 of these clients, put them on a 10 megabit link, and then we will ask them to stream the same thing. What you would normally expect to have each client use about 1 megabit per second fair share of the bandwidth, right? There are 10 clients and there's a 10 megabit link, and they're all identical clients. I'm not even talking about different clients from different vendors. And this is what the Smooth Streaming client did at that time. This is again about 2011-12 time frame. As you can see, since they are not aware of each other, they just try to fetch as high bandwidth as possible, right? And then obviously they are not going to be able to sustain it for a long time, so they need to downshift again. And then eventually they'll try again, and this is the mess we get. If this is something you are paying for, you will stop paying for this because the quality is absolutely a disaster, right? It's not just a bitrate change, but it's also the resolution change. When you look at this video, it looks really awful. Nobody was going to pay for this. Conviva, they publish these experience reports every year. Lots of reports are still being reported by analyzing millions of streams around the world. So there are still buffering issues, there are still glitch issues, there are still low resolution, low bitrate issues. You think that you have Google Fiber to your home, you have a decent 65 4K Samsung TV, but you get crappy quality at 1 megabit per second. That's not avoidable at all. Now, we looked into deeper to this problem and we realized that the main problem existed because of the control loops in this streaming application. We have a control loop that is trying to control the request response paradigm at the HTTP layer, which is developed by the vendor. And then there's this TCP congestion control, rate control, as well as the flow control running on the TCP layer provided by the OS provider. Now, the actual data transmission is happening at the TCP layer, but what you are trying to adapt to the network conditions is happening at the HTTP layer. And as it would happen in a company where there are two bosses, things go south when this happens. So this is obviously showing one TCP connection, but the problem is even worse when you have multiple TCP connections open to different servers or the same server over multiple TCP connections. One way to avoid, if you are opening multiple TCPs to the same server, you can use multipath TCP, which is an experimental RFC now coming out of IETF, which makes TCPs share the congestion state, which means we are going to be doing a better job. But if you are talking to multiple TCP servers, different servers, then you are out of luck. TCPs are not going to be coordinated, and things will start falling apart. Now, why people do that? There are many reasons. Because using multiple concurrent TCPs will allow you probably get a larger share of the bandwidth, where you shouldn't actually, because if everybody does that, nobody's going to gain anything. It helps with the head-of-line blocking that we have with the HTTP TCP connections. It also allows you to fetch multiple subportions of each segment, which Move networks did really, they were a really good example. And another, maybe one of the most important advantages of using multiple TCP connections is that if one of the TCPs goes to slow start mode because of a timeout, for example, you will switch to another working TCP connection without waiting for extra slow start period, which is really detrimental to video quality. But the research has shown that you need to be really careful with using multiple TCPs. If you are not careful about this, you will start actually deteriorating your performance, and not just yours, and you will also harm other streaming players. So a year later, we published another paper where we explained why this was all happening. So this is just a diagram that shows why it is happening this way. HTTP traffic by default is an on-off traffic. There's an on-off regime, right? If the on periods are aligned or partial overlapping or totally non-overlapping, the performance, the throughput observations by the clients are going to be different at each state. And this causes frequent upshifts and downshifts across clients. And this means there will be quality instability. Well, if you always stick with the scenario in C, where there's a full overlap, and every client is going to measure more or less the same throughput, let's say half of the bandwidth, right, the capacity of the line, well, maybe that will avoid the quality instability issue, but then you will get underutilization for the service provider, which is also not something we want. If you're in scenario A, you will get the actual bandwidth you can get from the line, but then this will indicate that eventually you will experience some instability because you cannot stay in scenario A all the time. Eventually you will switch to B, and then you will come to C, and then eventually you will fall back, and then this cycle will just continue. Why this is happening? This is exactly happening because how TCP was designed. Just like TCP cannot figure out how much bandwidth to use, right? The share of the network bandwidth, it needs to experience a packet loss before it can detect that. We have the same problem here. Clients cannot figure out how much bandwidth to use until they use too much. So you always need to make an accident before you can determine how fast your car can go, right? How we can solve this problem? Well, there's a problem, and we need to solve that. We identified 3 approaches, and over the years, we implemented each of these in different environments. First of all, the easiest approach is fix the clients. There are a bunch of different algorithms out there that were published by ACM, IEEE in these multimedia-related conferences that you can find from Cisco, Akamai, from universities around the world, and this sort of thing. Well, you can do this, and fixing the client actually helps a great deal. The only problem is that it only helps if everybody implements your own client, right? If somebody else is still using their own client and they don't follow the same rules, well, there will still be some problems in your network. The second approach, we were particularly interested in at Cisco while I was still at Cisco. Can we actually use some network intelligence to make this work better? You can apply some quality of service schemes in the core or the edge of the network. You can use some SDN tools, program your access network to give certain bandwidth to individual streams and so on. That's doable, and we have shown some results for that. And the third option is, enable a control plane where the clients can actually communicate with each other, or the clients can communicate to a third-party analytics server or the origin server so that they can do a better decision when they are asking data from the server. And this was standardized by MPEG in Dash, which is the part 5 server and network assisted Dash. There are some open source implementations for this. So if you're interested, I can point you in the right direction. So when you look at the OTT issues today in the field, obviously there are a lot of advancements like the codecs, the clients, DRMs, all that stuff, right? But we still have some issues. There are content format issues, which I'm not going to get into details. There are platform issues, which is also a very big deal, but that's not really within the theme of this talk. On the client side, we have a lot more issues, actually. Codec incompatibility, partial profile support. Yes, right, you can support Dash, but which profile, which features, and so on. What happens when you are switching from one bitrate to another bitrate? What if there are serious glitches, right? I mean, that shouldn't happen. Audio discontinuities, edge splicing problems, like when you are getting that, maybe the screen is gonna black out for a few seconds or not, that might really piss you off. Long-term playback instability, the audio video sync issues, all kinds of stuff. So, I mean, we are getting there. We are working on different organizations to hopefully come up with certain client models so that everybody can actually test against those conditions and identify the issues before the clients are rolled out into the field. Now, because of all those issues, and to find who is the one to blame, we need the analytics. Many people ignore this fact, but when you have a service that fails, the client is going to get really upset, right? The viewer actually, and then is going to finger point some guy to blame, but then they'll just keep circulating among themselves. Is it the OS to blame, service provider, the video CDN provider? Is it Netflix? Is it Apple? Is it Samsung? Or is it the app developer? To answer this question adequately, you need certain analytics data from the clients. Yes, right? Dash defined lots of different metrics, and there is a lot of work going on in CTA as well in R4 Working Group 20, if you're interested in following that work. A couple of new cool features that I would like to see being deployed in the field. These are all experimental features, but we are getting there. And a couple of years ago, Netflix came up with this idea called content-based encoding. We shouldn't be using the same bitrate ladder for all kinds of content. Well, yeah, I was really surprised that they were still doing that at that time. They said that cartoons, kids, or sports, they all require different codec bitrate ladders. Well, that's obvious. But the problem is not just that, right? And within a single stream, you can have different segments with different complexities, which means they will have a different R&D curve, right, rate distortion curve. If you would like to use the same bitrate across all segments in the same representation, you are going to get a variable quality. If you want to avoid that, obviously, you need to change the bitrate across the segments to get a more consistent quality. And that's what we have for, right, VBR, variable bitrate encoding. Well, doing VBR encoding could be easy, but streaming VBR content is not really that easy. I'll show you one example. So let's say this is my content, and there are segments for every 2 seconds. Segment sizes are more or less the same because I'm just following the one of the rule of thumbs saying that the bitrate variability shouldn't exceed 10%, which was given by Apple until very lately. So the segment quality, obviously, if I have a different segment qualities, the segment quality is going to vary, right? For some segments, the quality is going to increase. For some other segments, the quality will decrease. Why? Because I'm using the same bitrate for different complexities. Now, that's not really nice. Even if you are doing a good job in terms of adapting to network conditions, if you are even streaming at a high bitrate, you might still have these issues. And the viewer who is actually viewing the content will still get upset, no matter what you do, right? So, we don't want that. We don't like this. And we want to fix this problem. OK, let's do VBR encoding, right? So what I do is, based on the segment complexity, I can adjust the bitrate using this CRF flag, for example, in X265. In that case, what I'm going to get is, for some easy segments, right, the bitrate is going to be smaller, which means segment size is going to be smaller. For complex scenes, the segment sizes are going to be a lot larger. Now, at the end, what's going to happen is the segment quality hopefully is going to stay more or less the same. It cannot be perfectly constant, but that's not what we want anyway. Now, the good thing here is I was able to reduce the segment size for certain segments, and I used those saved bits for encoding bigger segments because they have larger complexity, right? So more or less, even if I stick with the same bitrate budget, now I am able to actually achieve a much higher average quality. But on top of that, the quality variation is so small so that even if I do some adaptation in the network, I will still be able to get a more proper and more stable streaming quality. Now, VBR encoding, as I said, is easy. But streaming VBR content is not really that easy. If you have significant segment size changes for your content over time, well, the client might get really upset. If you test VBR encoded content with today's popular clients, most of them will actually fail if you let the bitrate variation over 200%. So if you let your bitrate double for certain segments, most of the clients will just bark off, and then they will just go crazy. They will get confused. So content-aware encoding, which Netflix is proposing, is not exactly the same thing as content-aware streaming. And I'm sure we will get some more discussion on this in the afternoon. So this is a paper that we published before I left Cisco, how we are going to be able to do consistent quality streaming rather than adaptive streaming, right? At the end, remember, the viewer doesn't care about adaptive streaming. It just wants decent quality and hopefully consistent quality. So multiple representations have, on the server, we have multiple representations. And even if I have a fixed network, let's say 2.5 megabit per second, a stupid dummy CBR client will just always stick with the 2 megabit, or maybe occasionally mix 2 and 3 megabit per second to stay around the 2.5 megabit per second bandwidth limit, right? But a smarter client will actually look into the complexities or the quality levels of each segment and the sizes of each segment, and then it can, cherry pick the individual segments to deliver an overall better quality video. Now, that idea worked pretty well. We had a decent demo. It works really well, mostly for on-demand content. It's not really that easy to do it for live content, but for on-demand, you can really do magic. Now, that idea was actually simple. The next project we started working on was how we can do this optimization across streams. Now, let's say you're a service provider, Comcast, Time Warner, or Deutsche Telekom, who knows, right? And you have certain limited bandwidth to offer to your customers. So on the left-hand side, I can still do optimization within a single stream per client, right? The guy is streaming a video, I can still do some optimization across segments. But what is more challenging, and probably is going to be a lot more useful, is if I can do the same optimization or similar type of optimization across streams going through my network. Let's say I have a 10 gigabit pipe, right? And I wanna stream over 1,000 channels on that. Now, I don't want to give the same bitrate across all the TV channels, right? Because they are not all equal. CNN is not the same as ESPN, or it's not the same as HBO or C-SPAN, right? So you got to do this carefully, and you don't want to do this blindly either, because at the end, it's going to affect a lot of users. Doing that is not easy. Do I have a working implementation? No, we have a prototype, but it wasn't really a full-fledged product until now. So, I wanted to cover a lot of topics in a very short amount of time. Are there any questions? Yes, sir.
So if I have multiple users in the home all trying to do some streaming, maybe let's say your example, they're all using the same service, Netflix. Does it make sense then for the clients to communicate in the home and do some form of statistical multiplexing?
Well, it might, but there are a lot of people saying that it goes against the argument of clients-based streaming, right? I mean, we don't want to have a central controller, or we don't want anybody to tell what the clients should do. But I agree with you, some sort of coordination probably would help. So that's what motivated us doing this part 5 for Dash, server and network assisted Dash. So if there's a smarter home gateway device that can actually understand what's going on inside the home network, it's not just Netflix. It could be YouTube. It could be a bunch of other video services. So it doesn't even have to talk to the client itself. By doing some certain QoS magics, it can direct the clients in the right direction. But that certainly needs to be carefully done. Again, what if you are trying to watch a World Cup final game on your 65-inch screen, whereas your wife wants to watch a stupid food show in the kitchen on her iPhone, right? What I'm saying is that we shouldn't be really sharing the bandwidth fairly, right? I mean, fairness, what does it mean, fairness? I mean, when I say fairness to people, everybody thinks of bitrate fairness. But that's not what we would like to have here. We would like to have maybe quality fairness, or, I don't know, maybe experience fairness, right? Right? I mean, or what if, we are 3 guys or 5 guys watching the sports game, and then there are 5 kids watching something else, right? So, I mean, the amount of scenarios is pretty much unlimited. But how you can actually make this work in practice, that goes to part 5 of Dash, send. You need to define the certain messages, and you need to implement the clients who will actually act on those messages so that they can do the proper thing. It's not easy, but there is some hope, yeah. Any other questions? Yes, sir.
So SIPD's will be coming out with a report on flow control for professional media streams.
Yep.
Cisco is very active.
Okay.
And I didn't hear anybody proposing -23009-5 as a openly standard cross-everything control protocol. We've got control protocols. We've got AES 70, we've got NMOS, we've got SIPD SD2071. I'm co-chair. So many protocols, we're trying to have fewer protocols, not more protocols. Should there be a unified control protocol, or at least something that wraps them all together? And if so, do I have to kidnap children? How do we get this together? Too many protocols is not
Well, I don't think you can. I mean, if you have friends in United Nations or something, maybe. But no, I mean, seriously, the scenario is quite different. Here, we would like to use send, part 5 of Dash for, exchanging certain messages between the Dash elements, right? What you are referring to is a professional grade video. I mean, that has nothing to do with the crappy Dash videos, right? I mean, that's entirely a different application. So eventually, yes, I understand. It will be really nice to have a unified control mechanism. By the way, in Dash, we don't say it's control, it's assistance, because people don't like it when we want to control the clients. We would like to assist them. They always have the right to ignore our recommendations. So yes, this syntax could be similar or compatible, or how we are going to secure the messages, the encryption or security authentication, authorization, they could be all similar or compatible. But at the end of the day, these are all being developed by different organizations, not necessarily by the same people. So I guess this is not very easy to coordinate. I agree with you, but and many people look at this problem because they need some sort of job security too. So if things were so simple, they wouldn't have their jobs. So, any other questions? I mean, there's a lot of stuff in this domain. Looks like I forgot to put the call for papers for this, but next year's MMC's conference is going to be in Amsterdam. Just like Colorado, wheat is also public in Amsterdam. So, no, but MMCs, Connext, Infocom, these are really nice venues where the people are actually publishing really good ideas. I hope that more and more people from industry, they get involved in this, and maybe they just borrow some ideas and see how they're going to be implemented in the real world. Okay, thank you.